In this lecture, I will discuss some of the applications of integration in physics, and in particular, I will be focusing on computing the work done by a force. And first, we need to introduce the concept of work. What exactly is work? Work is a concept from physics that captures the difference between moving a 10 kilogram object 10 meters and moving a 5 kilogram object, or since I drew it bigger, let's make it 15 kilogram object 10 meters. It seems like, while to an outsider it may look the same with just moving boxes 10 meters, but somehow moving 15 kilogram box is a little different from moving 10 kilogram box, and also moving 15 kilogram box 10 meters is different from moving 15 kilogram box 5 meters. So work is something that captures those differences. And also, I forgot to draw another case which we are not considering in this class, but all of those cases are different from when you're applying the force in some arbitrary direction. So for example, you can be moving a box, but you can apply a force to an angle, and that's going to be a whole different story. So you can still take the 15 kilogram box, but if you're applying the force and the direction of application of force is not the same as the direction of movement, that's going to be a whole different story. So work is a concept that captures all of these differences, and in general, this is something that we are not doing in this class, but in general, work is a force as a vector, dot product of it by displacement as a vector. In order for us to be able to use this formula, we have to learn vector calculus, which is outside of the scope of the one variable calculus that we're currently in. But if direction of the displacement and direction of force coincide, then the formula that we're mostly familiar with looks like this. It's the work being equal to the force times the displacement. W stands for work, F stands for force, D stands for displacement. And if displacement is the opposite to the direction of the force, then work will be negative. If force is the opposite to the direction of the displacement, then the work will also be negative. Now, what are the units of work? When force is measured in newtons, in that case, distance must be measured in meters. And if force is measured in pounds, then the distance must be measured in feet. And then the units for work, when we use Newton and meters, is newtons times meters, which we call joules. But if we're using pounds and feet, then the units are just foot-pounds. And I think they just called foot-pounds. There's no an alternative name for it. Now, we talked about the differences between force being a vector versus force being just a value when its direction coincides with the displacement. Now, when we're looking at the following graphical representation of force doing work, so here's the force, and in order for us to set the stage, we have to introduce some sort of coordinate system. So let's imagine that all this action is happening along some axis, which we'll refer to as x-axis. And along this axis, let's assume that the force and displacement are acting along this line. And let's say if here's your force, and this force acting on some object displaced it from here to here, and this distance or this displacement can be described by letter D, then according to the previous formula, work is simply equal to force times distance. And in this formula, we have to assume that force is a constant. So when force is constant, in other words, when force doesn't depend on x in any way, then this is how we find the work. So one example of constant force will be the work done by lifting an object. So as you lift an object, and everybody has done this before, you take an object, you lift it, let's say 1 meter. The force required to lift an object of mass m, if we're talking about kilograms, will be mg, and this mg isn't going to change as you lift the object. So in this case, we will just compute the work by taking the constant force and multiply it by displacement d. However, this is not always going to be the case. Although this is the easiest case, we wish it was always the case, but it isn't going to be the case always. So the second case that we're more interested in, and this is where we get to use calculus, is when the force is not constant. And when the force is not constant, we say that we have a variable force. And in this case, we want to know how this force varies depending on the place of the object on that coordinate axis x. So we're going to say the variable force f of x. So this is the interesting case that we are going to focus on this class, and this is where we'll get to use the integration. So now that we understand the difference between applying a constant force and applying a variable force, let's once again set the stage and let's try to figure out the formula for computing the work done by a variable force acting along some line, which we'll refer to as the x-axis. And all axes have the origin, and let's say here we have a variable force. So that means the length of this vector changes as we move something along the x-axis. And let's say that we want to move something, or the force acting along this axis, and relocates something from the starting point A to the end point B. And the question is to find the work done by such force. And in order for us to use integration, we're going to be using the same procedure as we have done before. That is, we are going to create a partition. So that is, we are going to introduce n subintervals. And the width of each subinterval doesn't have to be the same, but it doesn't matter if it is the same or not, as long as the largest one goes to 0. So it works out nicer if we're going to make them the same. So let's make delta x to be this. Now we introduce the partition, so my x0 is the beginning, then we have x1, x2, my last term, my last value is xn, one before it is xn minus 1, and somewhere in the middle we are going to have the ith interval spanned by two values of x, which we label xi and as xi minus 1. And now delta x represents the width of each of these subintervals. So this is delta x, this is delta x, this is delta x. And here's the first statement. The work done by a force to relocate the object from A to B is the sum of all the works. So it's the sum of the work done to relocate the object from x0 to x1, then from x1 to x2, and so on. So what we really want to do is we want to focus on finding the work done on the ith subinterval. And the work done on the ith subinterval, if delta x is 0, so that subinterval is very small, and on that subinterval it is fair to assume that f of x doesn't change much. So it is fair to assume that on each subinterval f of x is constant, and that means that the work done by a force on the ith subinterval is equal to the force evaluated at some point on that interval. Because that interval is so small, it doesn't matter which point we pick, but we do have to calculate that force on that interval, and it is multiplied by the displacement, but displacement is delta x. So this is the work done on each subinterval. Now the total work will be equal to the sum of these works but it's not going to be equal to exactly that. Again, the exact work will be equal to approximately that. So if you want to actually find the exact work, then you have to find the limit. So as you set the limit, n must go to infinity. And here's the formula. But this formula can be recognized as a Riemann sum, and as a Riemann sum, this formula represents an integral from a to b of f of x dx. So the formula for finding the work done by a variable force to move the object from a to b, if the force is given to us as a function of x, then the formula for the work is this definite integral. And this is the first formula. And before we move on, I want to kind of take another look at this formula. So here's the formula. And why is this actually a very nice formula? We have to take a moment to appreciate this formula. Because if it allows us to compute the work when f is variable, but also if f is constant. So f is variable means we have f of x, but if f is constant, that means we just have f that doesn't depend on anything. If f is constant, let's see what's going to happen here. We set up the integral, but remember f is a constant and it doesn't depend on x, and if it doesn't depend on x, we can just take it outside of the integral, and when you integrate 1, because that's what's left inside of the integral, what do you get? You get x evaluated from a to b. You get, by the fundamental theorem of calculus, b minus a. But b minus a is what? It's nothing but the displacement. So this formula not only it allows us to now compute the work done by a variable force, but it also allows us to compute when work is done by a constant force. So it pretty much covers both of the cases, which shows you that it kind of validates this formula if it works for a constant force as well as it works for a variable force. Now, with this in mind, now let's take a look at the first example. So let's say we have a 15 kilogram suitcase that is lifted 2 meters. What is work done by this, by the force lifting the suitcase? And first thing we have to recognize is that F here is constant, and as a constant, why is it a constant? Because by the amount by which we lift the suitcase is so insignificant that the weight of the suitcase doesn't change, and it's computed using the formula F is equal to mg, and the mass is 15. The g gravitational constant is 9.8 meters per second squared. So this is the force. I don't have a calculator with me, but if we multiply 15 by 9.8, I guess we can do it later. So how do we find the work? The work will be equal to the force times the displacement. So the force is 15 times 9.8, and displacement is 2 meters. So now putting it all in the calculator, we get 15 times 9.8 times 2, it's equal to 294. And the units are joules. This is example of a constant force. Now, let's take a look at this example. In this example, we have a variable force, and the force depends on the value of x. So in this case, to find the work, we are going to set up an integral from 6 to 7, and we're going to integrate f of x with respect to x. It is as simple as that, as long as you recognize this setup. You have some force acting along some x-axis, and if you happen to know the dependency of the force on the x value, then it's as simple as setting up this integral. So have an integral from 6 to 7 of 9x squared plus 3, and we use all the knowledge of integration that we have. So 3x cubed plus 3x from 6 to 7. So 3 times 7 cubed plus 3 times 7 minus 3 times 6 cubed plus 3 times 6. And I don't know if we want to actually compute this. So if I just tell you the answer is 384, if you don't believe me, check. If I'm wrong, let me know. But I think this is what the computation will result in. And that's the introduction to computing the work done by a force. Now, there are actually many forces in physics that we learn, and one of the forces that we learn in standard physics course is the spring force. So what exactly is the spring force? So everybody have seen a spring. So a spring looks something like this. When it's neither stressed nor compressed, compressed or stretched, then it's said to be in equilibrium. Now, it does make sense to set the coordinate system in such a way that equilibrium corresponds to x equals 0, and the x-axis extends from the origin along the path of the spring when it's being extended. So if someone will extend the spring, it will be in positive direction, and if someone will compress the spring, then it will be in the negative direction. And it was the physicist named Hooke that observed that it takes a certain amount of force to hold a spring at a stretching or compressed position. And the amount of force is actually proportional to the displacement. And this is what we refer to as Hooke's law. And K in this equation represents the spring constant, and every spring has the spring constant. So some springs are a little tighter, some springs are a little looser, and physically that difference between tight and loose spring is described by a spring constant. So the tighter the spring, the larger the K will be. So the larger force will be needed to hold it in a stretched position or to compress it further. And once you know this, once you understand the Hooke's law, the work done by a force stretching the spring from A to B will be computed by setting up this integral from A to B of f of x dx, but f of x is just the kx, where k is a spring constant. So as long as the spring constant is given to you, we are capable of finding the work done by any force stretching or compressing the spring, again, as long as we have the value of k. So let's go ahead and try this example. So we have a force of 90 newtons being required to keep a spring stretched 5 meters from the equilibrium position. So let's draw a picture. We have some sort of spring. We automatically draw the x-axis with equilibrium being at the origin. And if it requires 90 newtons to stretch the spring 5 meters, so we're going to use that fact to compute k, because if it requires 90 newtons, so I'm using this equation here, F is equal to kx. So if it requires 90 newtons to keep a spring stretched at 5 meters, that means k is equal to 90 divided by 5, which is 18. And the units for the spring constant are actually known, but I don't think we actually bother with finding them ever, but it's got to be F divided by X, so it's got to be newtons per meter. So those are the units. So the units here are newtons per meter. So for every meter, it takes an additional 18 newtons to hold that spring. And now that we know K, the result is that we do have a formula for F as a function of X. So it's going to be 18x. So once again, all of this we done just by reading the first part of the first sentence. Now we're going to be reading the actual question, and as I read it, I'm going to set up the problem. So how much work in joules is done to stretch the spring 6 meters from equilibrium? So I literally interpret this question as finding the integral from 0 to 6 of f of x, but f of x, as we found right above, is just 18x dx. So it's a simple integral. It's going to be 9x squared evaluated from 0 to 6. So 9 times 6 squared minus 0 is going to be 6 squared is 36. 360 minus 36, what is it, 324? Again, if I'm wrong, let me know. But I actually have a calculator right here, so I'll compute it. 9 times 6 times 6 is 324. All right. So this is how we use the formula for computing the work for a variable force to compute the work done by a force to stretch a spring. The key here was in having the actual spring constant and finding it, which didn't require any calculus, but just algebra. All right, so let's switch gears and let's talk about how to compute the work done by a force lifting a cable with attached object. And let's set up the problem. We have some sort of building, and that building has the height, and from the top of that building we have some sort of a pulley set up here. So we're taking some object that hangs at the bottom of the cable. Imagine that being a chain. And the goal is to lift this object up up to the top of this building. Now, first we need to set up the coordinate system, and usually we set up the coordinate system with 0 being at the bottom and the x-axis being vertical, and the positive direction of the x-axis is going up. And now when we're lifting an object, we're still going to use the formula that we figured out earlier. It's going to be the integral from a to b of f of x dx. And a here will be the lowest position of the object, so whatever it was at the lowest, and b will be the height of the building, or where we take the object. So this is going to be my b. And why is the force here varies? Why is it a variable rather than a constant? And it could be for multiple reasons, but the main one is if you imagine a large object such as an anchor on a boat, and it usually attached to the boat with in ideal world it will be attached with something that doesn't have a weight, but in real life everything has a weight, whether it's a piece of string or whether it's a chain made of heavy links. But in real world everything has weight. So as you're pulling this cable up, it gets shorter and shorter. So as you would imagine, it gets lighter and lighter. So it makes it easier and easier to lift it. So the work that you do in the last bit of the lifting process is not quite the same as the work that you do for the first meter of this process. So the force varies because the weight of the cable changes as we lift the object. Also, sometimes in this type of problems in this class, you're going to be having a bucket that leaks, so which creates another variable there. So if your bucket leaks, the longer you lift it, the less weight it holds, so the lighter it becomes, so less force is needed to lift the bucket at the top in comparison to the bottom. So this is why we have to use this formula. This is why we can't just do F times B minus A. And the way we're going to approach this problem is we're going to simply focus on finding the force needed to lift this object attached to this cable. And frequently we're going to be having two forces to deal with. one force for the cable and one force for the bucket. And the force needed to lift the cable will depend on where you're at currently, right? So for example, if you are here at xi lifting the bucket for delta x, by the time you get to this point, you're gonna have much less of a cable, and therefore that creates a dependency between the force and the x value, and same applies for the bucket. So this is just a rough idea of what the formula, what it's like to compute this work. So let's go ahead and take a look at the example. And before we do an example, I need to mention that in some problems, they do say you can ignore the weight of the cable, and then you just have to focus on the weight of the bucket. In some problems, they do say that, hey, there is no bucket, it's just cable, so you're only focusing on the cable. And sometimes the weight of the bucket is constant, and sometimes it has a hole. So that creates like different variations. And in this lecture, I'm going to go over the worst case scenario. So if you can handle this one, I'm sure you can handle all others as well. So let's take a look at this problem. To set the stages, we're going to introduce the coordinate axis that goes from the bottom of the building to the top. That would be the positive direction. And this is going to be 0, and the top of the building is at 9. And now we're going to consider this cable with some weight attached at the bottom. And let's also notice that there's an extra meter of cable at the bottom to attach the bucket. And now, as we're lifting this whole cable with the bucket, the work done by the force will be equal to, according to our previous discussion, to the integral from a to b, where a is 0, b is 9. And it's going to be equal to the work done by a force lifting the cable together with a force lifting the bucket. And to find the force for lifting the cable, let's consider some subinterval of width delta x, and let's pick some representative on this subinterval x. Technically, I should be calling it xi star, but we can just refer to it as x. And when your bucket is x high above the ground, how much cable is left over there? And to find the cable, to find the force needed to lift that much cable, we use the following formula. The force is going to be equal to the length of the cable, which is 9 meters. But remember, we're x units above the ground, so it's going to be 9 minus x. But we have an extra 1 meter always, so it's going to be 10 minus x. And we're going to multiply the length by the linear density. That's the mass of the cable. And to find the force, we're going to multiply it by the gravitational constant g. So this is the relation between the force needed to lift the cable when the cable is x units above the ground. Now, for the bucket, so now we're going to be doing the same thing for the bucket. We need to consider the fact that the mass of the bucket initially is 41 kilograms, but it's losing 0.8 kilograms of sand for each meter. So if we're just looking at the relation between the mass of the bucket and the distance, we're going to see that the mass of the bucket initially is 41. But as you go up 1 meter, it losing 0.8 kilograms. So it's a linear relation between the height, the x, and the mass. And as a linear relation, it can be expressed as what? As the y-intercept minus the slope. The slope here is 0.8 kilograms per meter times x. So this is the formula that tells us how much is the bucket weigh at when it's x meters above the ground. So to find the force needed to lift this bucket, we're going to take the mass of the bucket, we're going to multiply it by g. And it seems like we are ready to set up the final integral. So the total work done by a force lifting a bucket and a cable as it is described in this problem can be found by computing the integral from 0 to 9 of this function. In this expression, g represents the gravitational constant, and it is equal to 9.8 meters per second squared. Now, since integration itself is not the objective of this lesson, I'm just going to plug this in Desmos and let Desmos or Wolfram Alpha do all the work. So I'm going to pause the video and I'll come back after I compute it. For the record, here's what I entered in Desmos, and here's the answer. So the amount of work needed to lift such cable with such weight is 5,239 0.8 joules. So if you can do this problem, you should be able to handle the problem in which the weight of the cable is negligible or the bucket doesn't leak. Alright, so let's take a look at another application, such as work done by pumping liquid from a tank. And the way that such problem is set up is we considering some three-dimensional tank, and in general it could be like a pool of water, so it's just three-dimensional object that has some unspecified shape in general, and it's filled with water, and it doesn't have to be filled all the way, but let's say it's filled with this much of water, and what we're doing here is we finding the work. Before we do that, we're finding the we're pumping the water out. So the goal is to empty the pool. And how do we do that? Well, one way is we can just stick a hose all the way to the bottom, and then that means every particle of water will have to travel this much of distance, right, in order to get out of that tank. So a better way to actually pump the water is there are pumps, floating pumps, that float in the water at the surface level, and they pump the water from the top. So that means only the bottom layer will have to travel the entire height of the pool. The first layer will only have to travel this much. So this is the most efficient way to pump the water. And the question is, how much work do we need? How much work is done by a force pumping the water out of the pool? The idea is, again, simple, and if you know integration. So the first thing we're going to do, we're going to set up the coordinate system with the origin being at the top, and the X is pointing down, and we're going to observe the fact that the pump pumps one layer at a time. So let's say we already pumped this dip, and we are at some xi sub star level, and the layer that we are considering is delta x tall. And the question is, let's just pump this layer out of the tank. How much work will it require? And the idea is that the amount of work required to pump just that layer can be computed by because that layer will have a constant mass, so the force will be constant, and we're going to be multiplying it by I apologize here, so delta x is not in the picture yet, but we're going to be multiplying it by the distance traveled, and the distance traveled here is x. Now, let's talk about the force. So the force needed to lift that much water depends on the mass of water, and it's going to be according to the formula, multiplied by the gravitational constant. But the mass of water now depends on the volume and the density of water in this way. But the volume of the layer of the water can be found by taking the area of this cross section and multiplying it by the height, which is delta x. So we're literally taking the height multiplying by the area of the cross section, which computes the volume of that cylinder. And this is where delta x comes into play. And what makes it interesting is that the area frequently depends on x, unless you have a cylindrical tank. And the trickiest part here will be to actually figure out the area of the cross section at depth x. That's the hardest part. But once you understood the area of the cross section, you know how to find the work done by a single to pump a single layer. Now the total work can be approximated by the sum of raising n layers, so it will be this. But if you want to know the exact value, you have to set it up as a limit, and n has to go to infinity, and I'm going to rearrange the terms inside of this sum as, I'm just going to put rho g x, and I put delta x at the end. And here we should recognize this as a Riemann sum. We're going to have from the bottom of the pool, whatever that is, so it's going to have its own height, to the top, whatever that beginning initial layer is, so let's just label it A and B. So we're going to be integrating from A to B, and we're going to be integrating this function, where A represents the cross-section of the tank at x units deep. Rho g are constants, they can be factored out, and the only thing that's left here is x and dx. So this is the formula for finding the work needed done by a force lifting, or rather pumping, the liquid out of some tank. And let's take a look at this following example. A tank has the shape of an inverted circular cone, and I'm going to draw the cone. and the height is 15 meters, so I need that to set up the coordinate axis, right? So we start, this is 0, this will be 15, and base radius is 4, so this is 4. The tank is filled with water to a height of 13 meters, so 13 meters means the starting level will be at 2. So we're going to be integrating from 2 to 15. And find the work required to empty the tank by pumping all of the water over the top of the tank. Use the fact, density of water is, everything is given. So to set this up, we're going to follow the same steps outlined in the previous conversation. And we're going to consider some level x. And at this level, we're going to be looking at pumping the layer of height delta x. And the formula for finding the work is the following. We're going to be integrating from a to b, rho g a of x times x dx. Rho g are constants. This is g, this is rho. X is the variable. The only thing we don't know is the area of this cross section, and to find the area we might have to do some geometry. So the area will be equal to pi r squared, where r represents this radius, and I'm going to draw that line segment, and we're going to consider this picture here. If this is 4 and this is r and this is altogether 15, but this is x, so this is 15. Then how do we find x? We're going to use the fact that these triangles are similar, so this triangle and this triangle are similar. Sorry, the small triangle and the large triangle are similar. That means 15 minus x over 15 is the same as r over 4, which allows us to find r as a function of x. So r will be equal to 4/15 of 15 minus x. And we can check this formula, because if x is equal to 15, r will be equal to 0. And that makes sense. When x equals 15, you are at the very bottom of this tank, so radius will be equal to 0. And when x is equal to 0, r will be equal to 4. So this is how we compute the r as a function of x, which means a of x will be equal to 4/15, 15 minus x, and all that squared, and we would multiply everything by pi. So now we're ready to find the work done by a force. The work will be equal to the integral from 2 to 15. Rho is 1000, g is 9.8. The area is pi 4/15 times 15 minus x, all that squared. Also, we multiply everything by x, and dx. And I am not going to do this by hand. I'm going to put it in Desmos to compute it. So let me press the pause button, and I'll be right back after I use Desmos. For the record, here's what I input in Desmos, and here's the answer that I got. So the answer is 841746886, but so the units here are joules, but if you are asked to answer the question using kilojoules, then the answer will be this. Okay, so we discussed few applications of integration in physics, and in particular we focused on computing the work done by a force.